Good evening. I'm Jay Farrell, President of the American Automatic Control Council. Welcome to the 2020 American Control Conference. This is the first ACC ever to be held in a fully online format. Planning for ACCs starts approximately 5 years in advance. So for the last 4 years, the operating committee was working to organize a successful on-site conference in the beautiful city of Denver. In late winter 2020, due to the COVID outbreak, they began to consider hybrid options. In early spring, considerations moved to a fully online format. This involved collaborating with Bob Judd to renegotiate the contract with the hotel and rebudgeting to offer lower registration rates. They worked together throughout late spring and early summer to prepare to host the ACC in its new online format. This slide shows the 2020 ACC Operating Committee. In addition to adjusting their work and personal lives for our new situation, this team has strenuously dedicated itself to organizing the 2020 ACC on behalf of ACC registrants, the control community, and the American Control Council. To all the members of the Operating Committee, thank you very much for your dedicated hard work. The ACC mission is to promote cooperation between the various segments of the automatic control profession in the U.S. and to represent the U.S. internationally. The ACC structure includes a board of directors, officers, committees, operating committees, review chairs, reviewers, and authors. The actual members of A squared C squared are the 9 professional societies listed on this slide. They collaborate to run A squared C squared on behalf of the control community. Each member society appoints one director to the A squared C squared board. The board makes the decisions that govern A squared C squared operations. The board of directors transacts its A squared C squared business in at least 2 meetings per year, plus electronically as may be necessary. The A squared C squared officers and committees organize and lead A squared C squared day-to-day operations. Main activities of A squared C squared include organizing the American Control Conferences, recognizing distinguished colleagues with awards, and collaborating with IFAC to enhance our profession worldwide. This slide shows information related to future ACCs. Next year's event will be led by George Chu in the city of New Orleans in late May. The other new information on this slide is that in 2024, Martha Grover will be bringing the ACC to Toronto, Canada in early July. And in 2025, General Chair Carolyn Beck will be bringing the ACC back to the beautiful city of Denver. All A squared C squared events are volunteer events. This is an opportunity for interested people to volunteer. You can get information from officers, general chairs. The Conference Activity Board is a wonderful place to start. Regarding awards, to give our distinguished colleagues the recognition that they deserve, the 2020 A squared C squared Awards ceremony will be held at ACC 2021. It is planned to be held before the opening reception on Tuesday, May 25th, so please adjust your travel plans accordingly. The 2021 A squared C squared Awards ceremony will be held as a separate event at its usual time on Thursday, May 27th. Your nominations for awards are always welcome, and that includes nominations for the 2021 Hugo Shuck Awards, which are based on papers presented at this year's ACC 2020, which starts today. The deadline for all awards nominations is December 1st, 2020. Nomination forms and award criteria can be found on the A squared C squared website. A squared C squared is the U.S. national member organization of the International Federation of Automatic Control. A squared C squared is a founding NMO of IFAC. It has hosted 2 World Congresses in 1975 and 1996. It sponsors IFAC events annually throughout the U.S. and supports volunteers, IFAC events, publications, committees, and leadership positions worldwide. Please join me in welcoming President of IFAC, Frank Allgauer. Thank you for your attention and for participating in this year's ACC. Good night.
Ladies and gentlemen, dear participants of the virtual American Control Conference 2020, dear friends, what a pity. When hearing a couple of years ago that ACC 2020 will take place in Denver, I was jumping from excitement and immediately told my students that we would like to submit papers to this conference. Such a beautiful city, so close to the exciting Rocky Mountains, and yes, I admit I was immediately thinking about a short vacation in connection with the conference. Just a few days of nice, relaxing downtime in the mountains, preferably together with some friends from around the globe. Vacation? Wait a moment, what was that again? Being together with friends and colleagues from other countries? Where is the manual for doing something like that? Things have changed. Most unfortunately, things have changed. And this time, definitely not to the better. The worldwide COVID-19 pandemic has been changing our personal and professional lives in never thought of ways. Indeed, what a pity. But will we just sit in our rooms and sulk? No, this wouldn't be the spirit of our forward-oriented automatic control community. Of course, we are trying to make the best out of the situation, and so have the ACC organizers that have transitioned ACC 2020 to a virtual online format within an admirably short time. A format that will allow us to still present and discuss technical papers and presentations and interact with each other. When looking at the program, this is again a great American Control Conference of high scientific level that proves once more the vitality of our field. Thanks to Santosh and Martha and their whole team for having first planned and organized an in-person event and then transitioned everything to a virtual online conference. Twice the amount of effort needed, and thus at least twice the thanks go to all people in the organizing committee. And congratulations to the American Automatic Control Council for having chosen such a wonderful team. Talking about the American Automatic Control Council, typically just called A²C², brings me back to the reason why I'm speaking to you today. A²C² is the US national member organization of the International Federation of Automatic Control, IFAC, and thus represents the United States of America within the IFAC Federation, or as we prefer to say, within the IFAC family. I am the president of IFAC since 3 years and for exactly 16 more days from the start of ACC 2020. On July 11, that is only 1 week after ACC 2020 will close, the 21st IFAC World Congress will start, and at the end of the World Congress, my term as IFAC president will come to an end. And you guessed it, the 21st IFAC World Congress will be a virtual online congress as well. Scheduled originally to take place in exciting Berlin, Germany, and now online. But very close to your home, wherever that is. Where your refrigerator is in walking distance, offering 24/7 buffet-style food instead of a struggle for survival at the conference buffet in the coffee breaks. At least this is one of the advantages of the corona crisis. And there are further advantages. For example, the registration fee for the first virtual IFAC World Congress, participation only, is just 80 euros. And I'm sure that the ACC organizers will forgive me to shamelessly advertise the World Congress. I want to invite you all to come and also visit the triennial IFAC World Congress with its 3,000 technical papers and video presentation. And altogether an exciting program with social interaction possibilities and with a global live track featuring plenary talks, tutorial sessions, industrial keynotes, demonstrator sessions, control competitions, and much more. But now, we focus again on ACC 2020 that we will enjoy over the next 3 days. Hoping that you are all doing well despite the corona situation, I am wishing us all interesting technical sessions, presentations and discussions. And I personally hope to meet many of you, at least virtually, in one or the other virtual session, at virtual booths, and in the virtual breakout rooms provided by the organizers during the course of the next couple of days. And then I am even more looking forward to seeing many of you again in person in the hopefully not so distant future. Enjoy ACC 2020, and last but not least, please stay healthy.
Good evening, I'm Mike Borello. I'm the Vice Chair of Industry and Applications, and it's my great pleasure in welcoming you all to the American Control Conference. Tonight, you're going to hear about one of the greatest scientific and technological endeavors humankind has ever achieved, the Laser Interferometer Gravitational-Wave Observatory, also known as LIGO. LIGO allows us to now view the universe in a very different way by detecting ripples in space-time caused by distant, often invisible cataclysmic events in space. I've been given the honor and privilege of introducing our speaker tonight that's played a key role in the LIGO collaboration, Mr. Dennis Coyne. Dennis is the chief engineer for the LIGO laboratory at the California Institute of Technology in Pasadena, California. Dennis is here tonight to talk about the significance of LIGO and about the control systems that played a huge role in achieving its Nobel Prize-winning success. Dennis spent 25 years leading the LIGO engineering team's efforts in the design and implementation of the first and second generation instruments that enable LIGO. Before Caltech, Dennis spent 15 years with Cayman Sciences Corporation in Massachusetts, Colorado, and New Mexico, having served various technical and managerial roles that well prepared him for the optomechatronic challenges imposed by LIGO. Prior to Cayman, Dennis worked several years at Bell Labs. Dennis received his BSME from University of Massachusetts, his MSME from UC Berkeley. He's a fellow of the American Society of Mechanical Engineers and a fellow of the American Physical Society. In 2018, he received the American Astronomical Society Lancelot M. Berkeley Prize. In 2017, as part of the LIGO collaboration, he accepted the Royal Astronomical Society Group Achievement Award, the Albert Einstein Medal, the Princess of Asturias Award for Technical and Scientific Research, and the American Astronomical Society Bruno Rossi Prize. In 2016, as part of the LIGO collaboration, he accepted the Optical Society of America's Foreman Team Engineering Excellence Award, the Breakthrough Prize in Fundamental Physics, and the Gruber Cosmology Prize. Dennis is also a member of Tau Beta Pi. So without further hesitation, let me introduce our speaker this evening, Dennis Coyne.
Hello, my name is Dennis Coyne, and it's my honor and pleasure to speak to you today about the LIGO project. LIGO stands for Laser Interferometer Gravitational-Wave Observatory, which I realize is quite a mouthful. I represent the LIGO scientific collaboration, founded in 1997. The LSC is currently comprised of about 1,400 scientists and engineers from over 100 institutions in 18 countries. The LIGO laboratory, which consists of about 200 personnel, is Caltech and MIT together. They're the group that built and now operate the observatories for the National Science Foundation. The observatories are shown in these aerial photos. On the left is the LIGO Hanford Observatory in the high desert of eastern Washington in the Hanford Tri-Cities area. On the right is the Livingston Observatory, which is in Livingston, Louisiana, midway between New Orleans and Baton Rouge. The two sites were chosen for many criteria, but One was that land was flat and relatively remote and quiet. Each interferometer observatory is shaped like an L with 4-kilometer long arms. These observatories are not alone. We're part of a growing global network. We operate in science mode and observational mode with our European partners who operate Virgo in Cascina, Italy, near Pisa. It's an EU collaboration that includes the United Kingdom, Germany, France, and Italy, and a few other countries. GEO is an interferometer observatory in Hanover, Germany. That's a collaboration between the United Kingdom and Germany. The Japanese have an underground cryogenic interferometer in the Kamioka mine that has begun observing this year, in fact. And we're working with our colleagues in India for a planned third LIGO instance in India. These are all second generation instruments. I'll mention plans for third generation at the end of the talk. So what are gravitational waves? Well, a little over 100 years ago, Albert Einstein realized that a consequence of his general theory of relativity was that waves or ripples in space-time would be created by accelerating masses. He immediately dismissed the idea of measuring those gravitational waves since the effect is exceedingly small. The best known and understood sources for gravitational waves are massive objects orbiting each other, such as stars, or as black holes, as depicted in this simulation. In Newtonian mechanics, these pairs of stars would orbit forever. However, according to general relativity, energy is lost from the system due to the emission of gravitational waves. And the result is that the orbiting pair inspiral into each other, in this case forming a larger black hole. In fact, Hulse and Taylor won the Nobel Prize in Physics in 1993 for observing, over a period of about 10 years, the change in orbital period of a binary pulsar system that matched general relativity quite well. So our mission is to directly observe these gravitational waves and then realize the astrophysical science that those observations enable. Well, we succeeded after about 40 years of research. We gave birth to gravitational wave astronomy in 2015 with the direct detection for the first time of a binary black hole merger event. This occurred 1.3 billion light years away. In the process of these roughly 30 solar mass objects combining, they release 3 solar masses of energy in accordance with E equals mc squared. In that last fraction of a second, they were 50 times brighter than the entire rest of the universe combined. The signal waveforms that we detected on both our instruments were consistent with Einstein's theory. For this discovery, the principals, Professor Barish and Thorne of Caltech and Professor Weiss of MIT, were awarded the 2017 Nobel Prize in Physics. Then, also in 2017, we detected, together with our Virgo colleagues, the first ever detection of the merger of 2 neutron stars, known as a kilonova event. Neutron stars are the remnants of supernova. And in this event that we detected, these 2 neutron stars coalesced, as they inspiraled together, approaching relativistic speeds, approaching about a third of the speed of light. When they combine, they create jets that emit gamma rays and heavy elements. These are the progenitors of gamma ray bursts. We detected the chirp waveform of this inspiral event as shown in this frequency time plot. About 1.7 seconds prior to orbiting satellites, the Fermi satellites detected the gamma ray first. Together with Virgo, we localized the position in the sky. It was consistent with the gamma ray satellite localization, but tighter, and tight enough to allow telescopes across the planet to search and find this new object. Over the course of the succeeding weeks and months, over 200 telescope projects collaborated on detecting the evolution, measuring the evolution of this event across the entire electromagnetic spectrum. And in the process, confirmed a widely held theory that the heavier elements are formed from these kilonova events. It's been estimated that the amount of gold and platinum produced in this one single event were hundreds of Earth masses. So what does this wave look like? What is its nature? It has two polarizations, like electromagnetic waves. They're created by accelerated masses, but the magnitude of the strain perturbation that this field produces varies as 1 over the speed of light to the 4th power, so it's exceedingly small. In fact, on the kilometer scale of our instruments, we need to be able to measure about 1/1000th the diameter of a nucleus or a proton. That's quite difficult measurement problem, of course. The other noteworthy aspect of the strain wave produced is that it compresses in one direction while it stretches in the opposite direction and then oscillates back and forth. So how do we go about detecting such a wave? Well, given the orthogonal nature of the compression and stretching, a Michelson interferometer is an ideal transducer. At its heart, a Michelson interferometer is basically a laser that splits light 50-50 at a beam splitter, sends it down 2 arms, reflects it back, and is arranged to destructively interfere the returning light beams so that there's no signal out the dark port or out towards the sensor, as shown in this sketch in the upper right. A slight change in the length of one or the other arms that creates a difference in the lengths then creates a signal. You no longer have a perfect destructive interference. We need to make the arms quite long, hence 4-kilometer size of our interferometer, in order to increase the magnitude of the strain effect, because what we're actually measuring is displacement, not strain. So the longer the arm, the more the displacement that the strain induces, and 4 kilometers is a reasonable civil engineering limit. In addition, though, that's not enough. We resonate the light in the arm cavities. We keep it there by bouncing it back and forth and increasing the effective arm length by a factor of 200. In addition, because of the terrestrial environment that we're in, we don't attempt to measure at very low frequencies. Our measurement is an audio band, so 10 hertz to about 1 kilohertz. At these frequencies, the ground motion, the environment is relatively quiet and can be further isolated, as you'll see. And then finally, we need to select extremely low loss mechanical materials and be careful in the design so that we don't spoil the measurement with thermal noise polluting our spectrum. When viewed as a as a receiving antenna, the Michelson interferometer is nearly omnidirectional, which is good because we don't know where these sources are. They're all over the sky. On the other hand, it points out the need for a global network because we need to use multiple detectors to localize the source in the sky by triangulation, by the arrival time, and also by consideration of the polarization of the wave. So what does our actual interferometer look like? It's a bit more complex than the Michelson interferometer. First of all, we have to spatially filter the light, strip off the higher order modes, reduce pointing jitter. We do that through an input mode cleaner cavity. The light then proceeds into the interferometer, but we have to mode match the light to the resonant modes in the arm cavities, and that requires a telescope shown by the three mirrors in what's known as a power recycling cavity. The reason it's called power recycling cavity is that the light that would constructively add and go back towards the laser and would otherwise be dumped, rejected by the Faraday isolator shown in the diagram, we send back. We put in an input coupler, the power recycling mirror, and that gains us more light. The more light, the lower the noise for the instrument, the more sensitivity. And so we now have a coupled input cavity that we call the power recycling cavity, coupling to the two arm cavities. Likewise, on the signal recycling side, we need to mode match the beam coming out of from the interference of the two arms. We need to reduce its size, match it to photodetectors. But we can also recycle the signal, that is, amplify it by putting in another resonant cavity, and that's known as a signal recycling cavity. And then finally, the output, which is somewhat polluted by scattered light noise, which manifests itself in some higher order optical modes, is stripped out through an output mode cleaner before we sense the gravitational wave signal. The optics used, to give you a rough idea of the scale, these are 40 kilogram masses, 34 centimeters in diameter. They're super polished and ion being milled to less than 0.15 nanometers RMS deviation from the radius of curvature that we require for resonance in cavities. They're coated with very low loss, both optical and mechanical low loss coatings in order to provide a low enough noise measurement. The sensitivity of the instrument is commonly characterized in two different ways, either with a strain noise spectrum or in-spiral range. If you're an instrumentalist, you think of it in terms of the amplitude spectral density of strain or displacement, or in other words, the square root of the power spectral density. At high frequencies, we're limited by quantum shot noise, low frequencies by quantum radiation pressure noise. In between, we are limited by thermal noise, hence the need to have very low loss materials. If one considers, if you're an astronomer, you think of it in terms of the range to which this instrument is sensitive for detecting events. Our standard candle is the coalescence of a pair of 1.4 solar mass neutron stars, averaged over direction and orientation of their orbital plane relative to the interferometer plane. This is a plot of the measured noise budget of the interferometer. The upper blue curve shows what we refer to as the DARM spectrum, that is differential arm. the difference between the two arms, the gravitational wave channel. It corresponds in this measurement to 137 megaparsecs range to our standard candle. The solid green curve is the root sum square of all of the measured noise terms and their couplings, and it corresponds to about 149 megaparsecs. The difference, as you can see, it matches quite well at high frequencies and intermediate frequencies, but begins to deviate from the DARM spectrum at about 40 hertz. That gap represents some unknown noise entering into our system or coupling of unknown noise sources. And it's an area of active research. Note that the angular control noise, the solid red curve, as well as the darker blue solid curve near it, called Mitch or Michelson control noise, are quite high, approaching the DARM spectrum at low frequency at 20 hertz and below. So as we improve the instrument, these are going to become potentially dominant sources of noise at that frequency range. So let's move on to the principal control plans. The photo here gives you an idea of what the inside of the corner station looks like. It's comprised of a very large vacuum system. In fact, we have two of the world's largest ultra-high vacuum systems operating at 1 nanotorr. All of the sensitive optics and detectors are within that vacuum envelope. So I'll talk about the seismic isolation system, the suspension systems, the laser, the interferometer sensing and control, which provides length and angle control for the critical interferometer optics. And I won't have time to go into all of the auxiliary controls, but I'll mention squeezed vacuum injection. And I'll just mention in passing that, as you might expect, thermal deposition in the optics causes perturbations, distortions due to index of refraction changes and thermal expansion that has to be compensated for. So we have an adaptive optics system. We also get the higher order modes in the cavity. Optical modes can overlap with the high Q mechanical modes of the solid body resonances of the optics and synergistically pump energy into it, and we have to contend with controlling those modes. So moving on to seismic isolation, how do we achieve the isolation? We have three sequential stages that provide three sequential systems that provide 7 isolation stages from the ground to the test mass optics. The first 3 stages are a combination of active and passive control. The third stage, the quadruple pendulum suspension, is predominantly a passive isolation system. The first stage is outside the vacuum system. It's shown in dark blue in the CAD sketch to the right. It's known as the hydraulic external pre-isolator, or HEPI. At the top of each of those 4 piers are vertical and horizontal actuation and co-located sensing that do the first level of isolation of the platform. The range of the actuation with these custom designed laminar flow quiet hydraulic isolators is plus or minus 1 millimeter. And that provides isolation to everything inside the vacuum system. Inside the vacuum system are the internal seismic isolation stages, or ISI. On the left side of this view graph, you see a picture of that two-stage system on a test stand being integrated, and assembled and integrated and tested. On the right side is a single stage, very similar in design and construction, but a single stage that's put into our smaller chambers. So each of these first three stages have 6 degrees of freedom, 18 degrees of freedom then for each test mass vacuum chamber or optics table. The outer stage is actuated by a hydraulic actuator, as I mentioned. The inner stages use custom designed electromagnetic actuators. All stages use blended position and velocity sensing in both feed-forward and feedback control. We also use ground inertial sensing to essentially correct the relative displacement sensing of that first stage relative to the ground, relying upon the coherence of the ground in the first stage at low frequency. We also have a custom designed low frequency, low noise tilt sensor developed by the University of Washington that we use to correct tilt coupling to the horizontal seismometer, which is a common problem at low frequency. All degrees of freedom on these stages are controlled independently in a Cartesian basis. It's also worth noting that we isolate each optics table, each vacuum chamber independently of all the others, even though our optical cavities span multiple chambers. And so the coordinated control between those platforms is something that we're currently exploring. So this is an example of the transfer functions control loops for one mode on one stage of these three-stage seismic oscillation system. We have a loop gain of about 1,030 millihertz with a 40 hertz upper gain, upper unit of gain frequency. As you can see in the lower left plot of the ground noise spectrum, and then the isolated spectrum in the X and Y, that is the two horizontal directions, we achieve a factor of 3 orders of magnitude reduction at 10 hertz. The additional orders of magnitude reduction required are achieved by the subsequent quadruple pendulum suspension. We also, of course, have to contend with non-stationary disturbances. This becomes a trade-off between performance and robustness. Probably the prime example is earthquakes. We've implemented a warning system that predicts arrival time, strength, direction, likelihood of our losing lock, so that we can decide whether to alter the control loss into a more robust state. That the reason we do so is that losing lock to us is a big downtime or duty cycle penalty. We have to reacquire lock, and there's a required sequence that takes some amount of time to reestablish that ideal operating condition at low noise. In addition, during that time, the interferometer is cooling off, and so we have a thermal management problem as well to contend with. We also have robust error detection to prevent instability-induced damage to the suspension systems, and don't ask me how I know we need that. Moving on, the quadruple pendulum suspension is then attached to this three-stage seismic oscillation system. The quad pendulum was a significant contribution from the United Kingdom. Their effort was led by the University of Glasgow. They designed the system with observability and controllability in mind, so that 22 of the 24 pendulum modes can be sensor controlled from the top stage. The modes associated with vertical bounce of the lowest mass and roll of that mass that involves extension of the fused silica fibers in the monolithic stage bottom stage, are the ones that are not well coupled to the top stage. They also designed the system with low thermal noise in mind, so the last two stages on the main chain are monolithic. And I should point out here, there are two stages, a reaction chain and a main chain, and that's so that when one reacts on the main chain, you don't transfer and cause transmitted ground motion. This view shows on the left side the lower two masses that are a monolithic assembly. That is, they're completely comprised of fused silica, including the fibers which join the two. The fibers are 400 micron diameter. They're CO2 laser welded to standoffs that are silica bonded to the optic and the penultimate mass. And this, by this process, we achieve mechanical Qs, that is, quality factors for the resonances of 10 to the 8th and or better. The actuation on the quad suspension consists of voice coil actuation on the three upper stages with co-located shadow sensors. So there are magnets bonded to the masses on the main chain, the voice coil and shadow sensor on the reaction chain. The lowest mass, the optic, the test mass, is actuated upon with an electrostatic actuator. As you can see in the middle lower picture here, this has 4 quadrants to allow us to piston control as well as to impose pitch and yaw control on the optic. The damping loops are limited to feedback at the top stage so that we don't inject sensing noise down at the lower stages. We benefit from the vibration isolation afforded by the suspensions. I should point out, when I say suspension, these are not just pendulum suspensions, which provide horizontal isolation, but also the upper stages have cantilevered springs so that they are also mechanically isolated above the resonance of those suspensions, those vertical suspensions as well. The modes that are not terribly well controlled, coupled to the top mass, are damped by passive 2 mass dampers for these high Q modes. The performance is such that we have residual seismic noise that dominates below 1 hertz, but between 1 and 30 hertz, the sensor noise projected through the longitudinal damping loop dominates up to 30 hertz. But we managed to achieve our required 10 to the minus 19 meters per root hertz isolation at 10 hertz. The suspension also acts as the actuator for feedback from the interferometer sensing and control. The length and alignment signals are frequency split such that the higher frequency content is impressed on the test mass optic using the electrostatic actuator, but below 2 hertz, it's split to the upper stages. Moving on to the laser, This is a contribution from the Albert Einstein Institute in Germany. It's comprised of a neodymium-YAG oscillator, which serves as a very stable reference due to its monolithic nature. The neodymium-YAG crystal is both the laser medium and the resonator. The subsequent two stages of amplification inherit the frequency stability of that neodymium-YAG oscillator. We then put the light through what we refer to as a pre-mode cleaner. This serves to spatially filter the light that is strip off higher order modes, thereby improve beam quality and efficiency in coupling to the interferometer modes. It also reduces beam pointing jitter and filters power fluctuations at RF frequencies. There are pick-off beams, sample optical beams from the pre-mode cleaner that are used in feedback to stabilize the intensity fluctuations, and also for locking the NPRO, the non-planar ring oscillator source, to the reference, to a reference cavity. The first reference cavity that's locked to is on the optics or on the laser bench on the table. And then once the light is locked, that is resonant in the input mode cleaner cavity within the basic interferometer in the vacuum system, we take sample beams, pick-offs from that input mode cleaner and feed back in an outer loop for power and intensity stabilization, and to a acousto-optic modulator to frequency shift the reference for feedback to the non-planar ring oscillator. In other words, we make the laser follow the input mode cleaner cavity length as a reference because it's a more stable reference. And then ultimately, once the arm cavities are locked, they become the reference for servoing the frequency of the laser. Moving on to the interferometer sensing and control. The control objectives here are to bring the interferometer into a low noise operating state, maintain it at that state, and provide the gravitational wave signal. The photo here shows the output mode cleaner cavity and the gravitational wave photodetector optics. And this is on top of one of the smaller isolated cables. Well, first of all, how do we measure optical cavity length? If you consider a single linear optical cavity, as you separate the mirror distance, until you get very close to an integral number of wavelengths of the light you're trying to resonate in the cavity, you don't get any signal in reflection or transmission. And the narrowness of that signal is based on not just the wavelength of the light, but the finesse, the quality factor, if you will, of the cavity. And then even when you do get such a signal, when you're close to resonance, the signal is symmetric about the desired operating point. So it's not a linear signal. In order for ease of control and to linearize the feedback signal, we use a technique known as Pound-Drever-Hall locking. What we do is impress sidebands on the main laser beam such that they are anti-resonant in the cavity that we're trying to control. And then we demodulate the interference at the reflection port with at the beat frequency, the beat between the carrier, the main laser light, and the sidebands, and then we get a linear signal. That signal can either be fed back to do phase modulation on the light, or can be fed to an actuator on the optics to make the length of the cavity follow the frequency of the light. We have 5 resonant cavities: the power recycling cavity, signal recycling cavity, the Michelson or near Michelson split cavity, and the 2 arm cavities. We project these into common and differential arm cavities, and the average of the power and signal recycling cavities. These are the control degrees of freedom that we feed back to. The signals for doing this are, as I mentioned, the RF demodulated signals from various ports in the interferometer. The reflection port from the power recycling cavity, a pickoff beam within the power recycling cavity, and the so-called antisymmetric port, or the output port. And you can see in the table our bandwidths are on the order of tens to a couple of hundred hertz, with the exception of the feedback to the arm cavity common mode, which is fed back to the laser. That has a bandwidth of order 30 kilohertz, and is done with analog electronics. The other controls are all digital electronics. We also have an arm length stabilization system which helps with acquisition. What do I mean by acquisition? Well, you don't just switch on the interferometer and it all locks up. It would take too long to serendipitously have the optics moving through resonances. You must guide the interferometer to that operating condition, because we have multiple coupled cavities with very narrow line widths, in the order of 1 nanometer. So the sequence is that, first of all, we've implemented a green light arm length locking system. We call it the arm length stabilization system. We inject green light that's phase locked to the main laser frequency. We've defined the coatings on the test mass optics such that they're dichroic. They have specifications in both green and our near infrared 1064 wavelength. We have designed the system such that we have a lower finesse in green, so it's easier to lock the arm cavities to green light. And then we intentionally offset them from resonance of the near infrared light, so that we don't have to deal with coupling of the arm cavities to the near Michelson, with the dual recycle Michelson degrees of freedom. The power recycling cavity, signal recycling cavity, and the Michelson split cavity. Once we have stabilized the arms and offset them from resonance, we then lock those dual recycle Michelson degrees of freedom using modulation at 3 times the fundamental modulation frequencies, which were 9 and 45 megahertz. And then we reduce the arm offset and bring the entire interferometer into lock. At that point, we can do angle sensing. The same phase modulation, demodulation techniques used for length sensing are used with quadrant photodiodes to produce alignment wavefront sensors. The alignment signal is the interference between the fundamental transverse electromagnetic 0, Hermite-Gaussian component. That is the main Gaussian on axis resonant mode. The angular misalignments of the cavity induce TEM 01 and 10 modes, and we can detect those using this RF demodulated quadrant detector. Incidentally, before we even are able to lock up the cavities, of course, the optics have to be aligned close enough to be able to get resonance in the cavities, and we do that using optical levers. They're red lasers that basically have a transmitter receiver. They bounce off an optic and onto a quadrant detector, and you once you've established the initial pointing alignment to get close to the ideal alignment, you can go back to that as sort of a flywheel reference for the alignment. The control then takes pickoffs for basically the same pickoff beam approach used for length sensing. That is, on the reflected port, a pickoff in the power cycling cavity, and at the antisymmetric port, we implement wavefront sensors, 2 each, so that we can sample at Gauy phase of 0 and 90 degrees, and then use an admixture of either to get whatever Gauy phase we want. Gauy phase has to do with the phase of in the Gaussian beam. 0 is at the waist. 90 is far in the far field. We also add to this array of sensors quadrant photodetectors that look at the beam that's transmitted through the end test masses, as well as transmitted through the PR2 SR2 mirrors. That is 2 optics within the power and signal reception cavity. Those quadrant detectors are not RF demodulated. They give us centering information. And then we control the 26 degrees of freedom of the alignment by doing matrix transformation to take the signals that are most representative of the degrees of freedom. Basically, we rotate the sensing matrix into the actuation modal degrees of freedom. Those angular control modes or degrees of freedom are depicted here in the so-called hard and soft modes or degrees of freedom. In the table, it indicates the sensor and port that's used in the feedback, and the frequency and the phase, whether it's in phase or quadrature phase for the demodulation. All of the loops are of the order of a couple of hertz, except some of them are as low as a tenth of a hertz. In addition, as we get the frequency of these modes varies as the power in the cavity, the resonant power, changes as we ramp up the power. So that resonant mode in the system shifts, and in fact, the so-called soft mode can become unstable. So you need to contend with this in the servo control loops. Moving on to squeezed light. As I mentioned before, at high frequency, we're limited by shot noise, low frequency by photon radiation pressure. The Heisenberg uncertainty relation places a bound on the product of the uncertainty in phase and the uncertainty in amplitude. So if you reduce one, you have to increase the other. This is true even for the vacuum state. And so it's been realized for some time now that if we're able to squeeze the vacuum state, that is the zero point electric field state and inject that into the output port, we can reduce the quantum noise. And we've done that, as shown in the measurements of the noise floor in our instrument. We've achieved 3 dB of squeezing, and you can see a little bit of anti-squeeze. And the reason it's not as prominent is we're not at that time low frequency dominated by radiation pressure. There were other terms that were more prevalent, more dominant. This photo shows that in vacuum optical parametric oscillator, which achieves the squeezed vacuum performance. Moving on to the control and data system architecture, our systems get their timing derived from a GPS, global positioning. Our front-end computers are Linux real-time, multi-core server class. We use FiberLink PCIe I/O buses with 20-bit analog to digital and digital to analog converters. We have servo loop rates up to 65 kilohertz. We have synchronous deterministic operation to within a few microseconds. We also complement this system with slow controls handled by EtherCAT backhaul. Software side of things, we have software that we refer to as the real-time code generator. It uses the MATLAB Simulink graphical interface to sketch our control, and we use that then to generate the real-time front-end C code. We do our supervisory control and interface to the operators using EPICS, the Experimental Physics and Industrial Control System. This is used in the higher energy physics community quite a bit. This helps set the roughly 100,000 servo system parameters. We also have a Guardian state machine used for sequencing. It's a hierarchical distributed finite state machine. Each node executes a state graph for the subsystems. It has an interface to EPICS, and it's built on Python. So what does our future look like? Well, LIGO and Virgo have just completed an observing run where we have detected over 50 events, and we'll be publishing a revised catalog quite soon. Where both projects are working on upgrades leading to an observing run that we'll call 04 starting in 2022. This is targeted at principally improving the coatings so that we have reduced mechanical loss, lower thermal noise. That will improve the performance in the most sensitive frequency range. We're also planning to implement, working to implement frequency-dependent squeezing, by which I mean that we rotate the angle of squeezing so that we squeeze in phase quadrature at high frequency, but amplitude quadrature at low frequency. And the way we do this is by adding an optical filter cavity. CAGRA started observing in 2020 and will no doubt join us in 04. And as I mentioned, we're just starting to break ground on LIGO India Observatory that we hope we'll be observing in about 2025. In addition, in parallel, the community is working on third generation gravitational wave instruments. Voyager is a concept where we use the current LIGO facilities, but improve the instruments to take advantage of the capability of those facilities by going to cryogenic operation, using large order 200 kilogram silicon masses and 2-micron lasers. We're also looking at new facilities on a longer time scale. The US, the concept of Cosmic Explorer is to take the basic LIGO system, but put it on a 40 kilometer long arms as a first phase, and then incorporate Voyager technology in the second phase. The Europeans have a concept they refer to as the Einstein telescope, which is an underground 10-kilometer arm length system. And ESA and NASA are working on a space base gravitational wave detector known as LISA. LISA had a successful technology demonstrator launch recently. So the future for gravitational wave observation looks quite promising. And I think we're now at a point where LIGO can really benefit from the ACC community input and ideas. Why do I say that? Well, I think we've taken the low-hanging fruit, removed obvious errors or flaws in the instrument design. We've removed a lot of technical noise sources due to scattered light, for example. We're getting down close to the ultimate design performance limited by fundamental noise sources. And now we'll increasingly operate the interferometer, not have the opportunity to go back into the vacuum system and make major changes, but we'll always be able to change the control system and to tweak performance and robustness. Thank you for your attention.